Good day, folks. This is tutorial number 15 in a playlist that is called Dynamic Scenario and Animation Modeling with 3D Experience. This particular tutorial introduces the bushing functionality, and the main reason is that there is an axial spring feature there, functionality there, but as the name suggests, uh, axial spring does not ask for information about torsional stiffnesses, etc. So it's fairly basic for axial deformation. If you need torsional uh, springs, then you need to employ the bushing icon. Now, needless to say that these are going to be important when you do dynamic scenario calculations. Okay, so essentially, I'm going to solve this problem for you where a disk is attached by that shaft, for example, to the ceiling, and you displace the disk and let it vibrate back and forth. So basically, that shaft plays the role of a torsional spring. Now, this information is coming from a fundamental or basic vibrations textbook. So if you have the dimensions and everything, you can calculate the stiffness of that torsional spring based on what you see on the right-hand side. J is the mass moment of inertia of the disk, which is 1/2 mr squared, m being the mass of the disk, and r is the radius of the disk. And uh, Now the vibration, assuming that there's no damping here, uh, in a basic vibration book, you see that the governing equation of motion is this essentially rotational inertia is balanced by the torsional spring force. And if you take everything to one side, this is the equation of motion, which is the analog of mx double dot plus kx equal to 0, except that because we're dealing with torsion here, because we're dealing with rotation here, it's not m, it's j, and k is the torsional stiffness. Now, the natural frequency of this is square root of k over j, no damping here. And uh, what I'm going to do, I'm going to model this particular geometry for you. However, remember, I'm not going to model the shaft. What I do is to calculate the torsional stiffness of the shaft and then use it later on along with the disk that you see there. The details of the dimensions of the shaft are given here. So that gives you a torsional stiffness as you see up there. The details of the disk are given here. And these are actual dimensions that I'm going to model. And I'm going to assume that the material is a steel. Therefore, the mass of that, based on these dimensions, becomes actually 100 kilogram. And 1/2 mr squared, m being 100, 1/2 mr squared, you convert everything, is going to come out to be j equal to this. Okay. Now I'm going to do the problem initially with no damping. Okay, c equal to 0. Therefore, we can compare it with a calculation that I showed you a minute ago. Omega n can be calculated, and then once I do that, I come back and do it with a damping that's torsional damping that's specified here. Now, if the damping is 0, then the natural frequency is going to be up there, and the natural period is going to be there. And if there is a damping, then you have to do a bit of calculation here, and you're going to get the damp period of 0.664. Okay. Now, just to show you where these are coming from, here is my MathCAD worksheet. I know that I is 1.9, and I know that the mass is 100. Okay, and this K, I'm going to input it into the 3D experience, and later on I'm going to put if you, the top 3 lines is no damping. If you have a C equal to 5, for damping is introduced, then the period comes out to be this number. Uh, Actually, the one that below, the period of the damping is going to be 0.664, period of the undamped is going to be 0.652. Now, notice that I'm not modeling the shaft. However, because there's going to be a revolute joint between the disc and something up there, I'm going to create a stand which looks like that. Now, that stand is not the size of the shaft that I showed you a minute ago, but it really doesn't matter because that stand is going to stay stationary. It's going to stay fixed in space. It doesn't matter uh, what it is, what size it is, etc. Except that I have already calculated the torsional stiffness of the shaft, and I'm going to use that. And also notice that I have rotated the disc so that it's not aligned with the shaft up there, essentially the dummy shaft up there. There's a reason for that because we're talking about free vibration. Therefore, you need to have some offset between these planes. Okay, these two objects. So I'm thinking I'm using roughly 20 degrees. Small scale oscillation. Now, uh, because I'm using a Revolution usually have a command. However, I'm not going to assign any command because the this this displacement, this offset between the angle of these two parts by the 20 degrees that I've done essentially provides that rotational restoring force. Now here's what's going to happen. So notice that even when you use bushing, it's still called a spring, okay? However, the properties are given as the bushing property. And so here's, if you click on the icon bushing, it's going to ask you for two supports, support one and support two, and these must be axis system because the bushing is actually axis to axis system uh, uh, joint essentially, some kind of a joint like that. And notice that there's two tabs there. There's the elasticity tab where you specify the stiffness of the torsional spring, which I've shown you is 176 dot dot dot. And then there's a damping tab, which later on when I'm going to apply a damping of 5, these are both associated with MZ, I'm going to use that value. Okay. Now, so there's going to be a revolute joint, there's going to be a spring joint, which actually it is a bushing. Okay. And the properties of I have to specify the property of the dummy wall or support because it's a dynamic problem. It wants inertia about everything, but that's totally irrelevant. I'm going to use the properties of steel, but totally irrelevant and never used. And the disc is on the left side. I'm going to use properties of steel based on the dimensions that I have. It's going to be 100 kilogram. I also notice that line number 10 on the left table, it says 1.9, and that is the J that I calculated based on 1/2 mr squared. There's your 1.9. Okay. Now no excitation is needed because I'm offsetting this by so many degrees, 20 degrees, the two parts by 20 degrees. In a different tutorial, I will apply a harmonic torque applied to the disc, and there, of course, you also have excitation. Even if you don't have an offset between the two angles, because there's going to be an excitation, you can run a dynamic analysis. But not here, no excitation is needed. And I'm going to use this standard DASSL integrator. Remember, there's two of them. This is the one that I'm going to be using, and I'll do it over a period of uh, 1 second. Now, if you want to know about the bushing, you can go to the help or user assistance of the 3D experience, and you come across this page. And then you come down here at the very bottom, it says AI is the angle between two attachment points. Now, what the heck is that? In fact, this is all very vague and there's no theory manual. This is the only pretty much information that you get, and it's going to be tough. It's going to be, yeah. Okay, let's move on. So let's go ahead here. Okay, here is the 3D Experiences interface. So let me start with an assembly design, because we're dealing with essentially a mechanism. And right here, I'm going to insert my first part, which is going to be that wall, fictitious wall on the top or ceiling. 3D part, and I'm going to call this thing the wall. More appropriately, should be called ceiling. That's okay. call it wall and wall, and okay. Let's make it. It's just a cylinder. Double click on it. On this plane, I will sketch a circle of radius 0.05 meter. All right, exit. And pad it by some amount. For example, so let's make it. It really doesn't matter. I'll make it. Yeah, that's fine. Now, what I will do is I will create an access system here while I'm at it. Okay, let me create an access system. See now, where are we now? Under the model access system, it's going to put it at the global origin, which is there, and that's fine. There's no problem there. I'll just leave it the way it is, and then we go all the way to the top and insert our next 3D part, which is going to be the mass that's going to be uh, torsionally oscillating. Okay, so let me rename this thing to be I'll call it the mass. I'll call it rotary mass. Rotary mass. And you can make it anywhere you want, except that for me it's easier if I just go ahead and make it uh, as I'm moving along. So for example, on this bottom piece, I'm going to sketch a circle 0.0195 radius radius 0.195 that's the diameter. So let me put down 2 times 0.195. And I just noticed that the other fellow, I put down radius of 0.05, but that was diameter 0.05. So my mass is not gonna correspond to the mass table that I'm going to show you here, because I use a different dimension for where is that different dimension for the wall, but it really doesn't matter. Okay. It's not going to be 1, 2, 2, 1. It's going to be smaller. But anyway, let's exit. So here's the situation. I'm going to pad it. Not in the other direction, by the height of let me see now, what is that, 108 millimeter, or yeah, 0.108, sorry, 0.108 meter. Where is that? 0.108 meter. Good. So this is the correct size. Okay, now let me create an access system, but so that I can see things easier, I'm going to create a point down here and put the access system down below. So let's go ahead and make a point here in the middle of that bottom piece, right there. And now when I create my access system, I'm going to put it down there. The origin of it I can pick, and I'm going to pick it to be there so that I can distinguish it from thing up there. Now, the only thing is that I don't want this thing to be I don't want this thing to be aligned with that. I want to offset this axis system by roughly 20 degrees. So I'll put the cursor here, right click, rotation, put down 20 degrees, 20 degrees, doesn't matter, and then say OK. Okay, later on I'm going to come back and see what happened if you don't put that 20 degrees, or that offset angle between the two coordinate system. But we'll see that later on. Now, first of all, while you're at it, let's go ahead and fix the wall there. Wall under engineering connection, fix the wall, and then you create a revolute between the two pieces. So the template that I use, axis to axis, plane to plane, okay, and I'll do this. So the axis of that maybe the disc, and the axis of the wall, and the top plane of the disc, and the bottom plane of the wall there. And since I'm not going to be controlling this revolute joint, I don't need this last one. I'm just going to delete it. Don't need it. We say OK. And no to the contact detection. OK, good. So we have created, fixed something and created a revolute. And now we're going to go and create a bushing elements and things like that. But it cannot be done here because you don't see anything called bushing there. So let me actually also check here on their, uh, let's see if there is any bushing there we can use. No, you see, you don't see any bushing here. Yeah, okay. So let me close that. All right, so we go to the mechanical systems design, and if you scroll down, you see the axial spring and the bushing. Okay, the problem with axial spring is that you cannot specify the torsional stiffnesses. Okay, so you click on the bushing. Look at what it's asking you. The support, two support, and these supports might be the access system. So I use the wall access system and the rotary mass access system. Excuse me. And then there is two tabs here, elasticity. So click on it, MZ, and you put down the number that I had, 176.175. This was the torsional stiffness of that rod that was supporting the disc from the ceiling all the way to the disc. Okay, so and there's no damping here, so let's not worry about that. There's torsional stiffness, no damping. Okay, good. So notice that a spring element has been created here. Actually, it's a bushing you can see. Now let's go ahead and create our the inertial properties, mass and things like that. So while you're in mechanical system design, all the way to the right, weight definition, notice that nothing has been defined yet, red. So you select for example, the wall, and you click on the hyperlink, and then click on this checkbox there. So steel is going to be used. Now the reason that these numbers are different for the mass of the wall is different from what I had in the slides is because remember I had this top piece inadvertently. I specified the diameter instead of the radius, but that's okay. That's not going to participate in the calculation because it's stationary anyways. But you have to do it, otherwise you won't do it. And then you select the rotary mass, click on the hyperlink, and click on this checkbox here. It uses the properties of steel, which is about 100 kilogram. And then this 0.19 here is what I had in my slides. Okay, so we say, all right. So we specified the inertial properties of the structure, and therefore everything is defined 100%. Very good. Now, uh, let's check, create our mechanism. What is that? Mechanism representation. All right, it's done. And you click on this, it tells you what you have here. You have a fixed wall, a revolute, and a spring, which is our bushing. And then we say OK. All right. Now we switch to mechanical systems experience. This is where you actually do the simulation. We don't have to create a mechanism. That was already done. Okay, we click on it, say OK. Simulation is created. Now let's create our probe here. The probe, that's why I created a point there, because I want to, if I want to, for example, velocity here, etc., I can use that. Good. And now there is no need to do any of these excitations because the fact that we offset that thing by 20 degrees will actually create a restoring force, restoring torque, which makes motion possible. So you click on the dynamic scenario. First of all, the probe that I created, I send it to the right. The parameters, I'm going to be using DASSL algorithm. I'm going to do it over a 2-second interval, maybe 1.5. I don't know. Where I put it really doesn't matter. It's just that here I put down 1. Okay, well, I'll put down 1.5, no problem. And then we say OK, and then run it. You put the cursor there, right click, force compute, or you can go all the way to the right and click on that. It's entirely up to you. That's good. Now let's look at the reason it kind of oscillates, looks like it oscillates twice, is because I put down 1.5 seconds. Okay, you click on the results and deselect everything and show me the angular velocity of the probe that I created right there. You see this? What is the period here? This is one oscillation. This is not two oscillation. Going in one direction, stopping, and going in the other direction. So this is a period which is roughly 0.6566. You can go to the table and go find out roughly where it is. So notice that uh, this is the angular velocity of that point. You go to 0.6, kind of 6-ish. Things are getting smaller, 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 and then starts getting bigger and bigger. 0.66, so or 0.65-ish. So that can be compared with 0.652. Now, let me show you something. Uh, Let me go ahead and take, let me go and put damping, and then I come back and show you what happens if you don't put any 20 degrees angle, okay? So let's go here, close that, select the bushing, and damping, MZ, put down 5. That's what I wanted. So we say, okay. That's pretty much it, and then run. Now we have a damping, torsional damping coefficient of 5. So right click, force, okay. All right, go to view results, deselect everything, just show me the velocity, the angular velocity. Notice that the angular velocity is getting smaller and smaller. Now, what about this 20-degree thingy? Okay, so suppose I went and took away that 20 degrees away. Okay, either for the damped or the undamped case. It really doesn't matter. So I can double click on this. There we are. So I'm going to rotate above the Z axis by minus 20 degrees to put it back in the same place. And it aligns it with the wall. Minus 20. Notice that now they're aligned. Say okay. Now we go here and try to run it. Yes, there is damping here. If you don't like damping, we can just take it out. It really doesn't matter. But right click, run. Nothing. Doesn't move because there is no restoring force. If you look at the results, deselect everything and say, show me the angular velocity, it's going to be 0 because nothing is moving. All right. To convince you one more time, let's go ahead and double click on this. Let me rotate this thing by, I don't know, remember, this is small scale oscillation. The angle should not be very large, but I'll make it 40 degrees. Right click, rotation, about the Z axis. I don't know, maybe 40. You come up with the same period. At least you should be close to it. It rotated by 40. Go back here and run it. Yep. And let's check the period. What is that thing? Again, roughly 0.6. Now, remember, I didn't actually check this thing. This should match the right here, 0.66. Okay. So it is the same thing. Okay. The height, of course, is the height. Let me see now. The height, yeah, there will be different. Okay, will be different because if you give it more, give the disk more rotation, there is more energy stored in it, and then when it turns, it's going to convert into kinetic energy. Yeah, so that's fine. Anyway, that takes care of this. There will be a couple of more videos on bushing and some other issues, related issues that we'll do later on. Good luck.